In our last lecture, we introduced Kepler's laws. Basically, Kepler found, using observations by Tycho Brahe, that planets move around the Sun in orbits that resemble ellipses. That's his first law. His second is that the planets move faster when they're nearby and slower when they're further off. Today, we're going to emphasize his third law. Then, we're going to use part of that in order to start the discussion of Newton's laws, which were the laws that actually turned astronomy into astrophysics. Johannes Kepler was a sickly child that lost his good eyesight as a teen due to illness. Fortunately for us, that was after he already fell in love with astronomy. Still, he couldn't observe anything in the night sky and had to rely on others for data. He excelled in math and astrology, the ancient art of casting horoscopes, art or religion. Horoscopes for Kepler was very important. He would use much of his career trying to relate planets, the moon, the sun, and the weather, and how things influence your own life. That was not even one of his strangest ideas. Anyways, at age 30, he was teaching math in a small private regular school, not a university, and started corresponding and collaborating with Tycho Brahe, one of the most unlikely collaborations in history. For one thing, Kepler disparaged Tycho's weird model where Earth was in the middle, the Sun was going around the Earth, and everything was going around the Sun. Kepler recently published model of the Platonic solids was disparaged by Tycho. Both, though, had the integrity to accept each other's failings and admire each other's skills. Otherwise, science might have languished for hundreds of years to come. Kepler landing his hands on Tycho's Mars observation made it possible for him to come up with his laws, especially the first two laws. It was no coincidence that Kepler did not deduce the elliptical orbits of planets from observations of Mercury. Those are the observations that I've shown you in the previous lecture. That's because they were not available to him after Tycho's death. Tycho's descendants did not want Kepler to have that. So, Tycho's amazingly meticulous observations were the ones that were used in order to deduce the elliptical motion of Mars. Now remember forever, guys, observations from your rectal temperature to the cell phone frequency that you are holding to the Big Bang echoes now are the ones that determine what theories are. I've got a theory means that tens of thousands of observations agreed with your hypothesis to begin with. So here's a scientific law that took a lot of effort. This is Kepler's third law. What I'd like you to do is to take into consideration what this law says by taking out your calculator and doing some calculations. Earth's orbit takes 1 year. Earth's distance from the Sun in astronomical units is defined as 1. Kepler said that take the first, meaning the period, and square it. Take the second, meaning the distance, and cube it, and you get the same. And you're saying to yourself, 1 square equals 1 cube, duh, of course. Okay, now let's do the same exact thing with Jupiter. Jupiter, the largest of planets, is at 5.2 times the distance of Earth from the Sun. Take, for example, 5. 5 times 5 is 25, times 5 is 125. That's pretty darn close to 11 times 11, which is 121. Okay, 125 and 121 are pretty close. which means 5 cubed, is not too far from 11 square. Now, how long does it take for Jupiter to orbit the Sun? What that means is that how long until Jupiter is not in retrograde, because retrograde is in retrograde every little bit over a year. Actually, how long until Jupiter is in retrograde in the same exact constellation again, and that's going to tell you pretty much its period. So that's basically what Kepler did with all of the planets in the table you've seen in front of you. Mercury, Venus, Earth, Mars, Jupiter, Saturn. He did not see Uranus and Neptune, but as you may see, it is big as well. Here we go. We have a hypothesis. The hypothesis has been plenty supported, and that's great because we're going to use it next for something that's very contemporary. The following graph is very recent. This is a picture of planets that are not orbiting our Sun, but rather orbiting thousands of stars throughout the galaxy, all of which we now know have their own planets. There are various techniques by which we found that, but we only found those planets that orbit other suns in 1995 onwards. Not in Kepler's time, but in our own lifetime. On the y-axis, you have the eccentricity, which means all of the dots that have 0 lined up with them are orbits that are circular. Everything that's above is elliptical. Very elliptical are the numbers that are very close to 1. The colors represent the mass of that planet that's orbiting its Sun. Of course, since they're so far away, it's way easier for us to observe planets that would be much more massive than the mass of Jupiter, but we've seen actually a whole slew of types of planets orbiting those stars. And all of them absolutely obey Kepler's laws. So, Kepler's laws work for the planets orbiting our Sun and for planets around other stars. But why do they make sense at all? What is it that makes them go? What is it that's responsible for their incredible, interesting orbits? Kepler himself had an answer that may surprise you. He thought this was the result of a heavenly music. Basically, every ellipse was determined by its average radius, its eccentricity, its tilt, and so up to 5 numbers determined that planet's motion, actually 6 if we're a bit more careful. Those 6 numbers for Kepler made for 6 notes. Basically, those notes were the heavenly notes. We no longer believe in Kepler's harmonies of the spheres, but you just have to note that this is how science begins. We come up with a hypothesis. This hypothesis of Kepler, of course, has never been supported. Descartes, on the other hand, said, let's make more sense of it. The closer you are to the Sun, the more of the Sun eddies, the more of the Sun effect on everything around it is going to happen. This is kind of like being very near some sort of a turbulent current. And the closer you are to the turbulent current, the more influenced you are. The Sun itself creates some sort of eddies right around it. That's what causes Mercury to move faster, and that's what causes Venus, Earth, Mars, Jupiter, and Saturn to move less and less because you're further out from the eddies. These were by now proved wrong as well, but at Descartes' time they made plenty sense. Descartes, same guy that said, I think therefore I am. Then came Newton, and his work is what we're using almost until the present day. Ends up that it's just as weird, and yet it works. Isaac Newton was perhaps the greatest scientist of all time. His father was a farmer that died before Newton was born. Newton was a baby premature and small. His mom remarried shortly afterwards to a clergyman that Newton hated. Newton never studied math in his regular pre-university education. In Cambridge, where he went to, they taught Aristotelian and ancient Greek math and science, so he taught himself the works of Copernicus, Kepler, Galileo, and Descartes. He then proceeded to invent physics, the physics that is used nowadays by every civil and mechanical engineer. Then he invented calculus together with Leibniz at the same time. He improved dramatically upon optics, and he basically merged physics and astronomy. He himself was never married. Not to be too bored, I guess, he became the head of the Royal Astronomical Society, and in that role made the life of other scientists such as Robert Hooke and Leibniz hell. He also headed the Royal Mint, basically minting coins, and he played the detective to help convict, hang, and quarter forgers. He was a prolific theologian and rejected the worship of Jesus as God, but strongly believed in benevolent Christian God. He spent half his time on alchemy, a field of study that at the time was trying to turn lead into gold.
Newton's universal gravitation was a synthesis of the fact that the sun is acting on the earth and the earth is acting on the moon. As a result, he assumed that the earth is acting back on the sun and the moon is acting back on the earth. Taking that into account, he invented universal gravitation and Newton's famous three laws. Newton's three laws are actually not laws that were invented or found out by Newton, at least not the first and the second. The first law was first discovered by Avicenna or Ibn Sina, an Arab scientist in the 10th century in the area between Iran and Iraq. Galileo then rediscovered it and started the second law. The first law is that things keep on moving if you don't act on it. In empty space, you don't need to push anything for it to keep on moving. The second law is that objects do speed up if you act on them. So in the same empty space, if you get the rocket to fire, it will not keep the same speed. It will either speed up or change direction. And the third law is that the force by an object on another is the same as the force by the second on the first. For example, first, the force by the sun on the earth, same as by the earth on the sun. So why is the sun not moving much? Because it's much more massive. Same with the moon. The moon is going around the earth. Why is the earth not moving around the moon? Because it's much more massive. However, lo and behold, some influence by the moon is detectable. For example, the tides.
What's amazing about Newton's laws is that they right away manage to explain the tides, the precession of the equinoxes, Halley's Comet, and Earth's oblateness, based on the same laws that explain the motion of planets around the Sun. We will spend more time on that in our next lecture.